So magnetic fields are created by moving charges, and the simplest case of that is a single point charge moving at a constant velocity. So in this case, the formula for the magnetic field that it creates, if we go a distance from the moving charge, then the magnetic field is going to be mu naught over 4 pi, which is a constant, multiplied by q, the charge, times v cross a hat, where v is the velocity and a hat is a unit vector that just points in the direction of wherever we're trying to find the magnetic field. And then over a squared, which again is the distance from the charge to the point where we're trying to find the field. So again, a hat is a unit vector, which means it has a magnitude of 1. So its only purpose is to point in the direction of the, it points from the charge to the point where we're trying to find the magnetic field. So in this case, if the angle between v and a hat is theta, then all we have to do is replace v cross a hat with v sine theta, because again, a unit vector always has a magnitude of 1. So its only purpose is to indicate this angle. If we were trying to find the magnetic field, say at this point, directly above the charge, then a hat would be pointing directly up, and this angle would be 90 degrees. So v cross a hat would just be v, since they are already perpendicular. And so mu naught is a constant, which is 4 pi times 10 to the negative 7th. So you use this formula to calculate the strength of the magnetic field around this moving charge. And if you want to know what they look like, they're going to form concentric circles around this moving charge. So this is kind of a view from behind. So the circles would be going outward and all rotating in the same. The magnetic field lines would be circles and all going in the same direction. And you can get the direction of these field lines by using a form of the right-hand rule. So you make a fist with your thumb and point your thumb straight up. And if you point your thumb in the direction that the charge is moving in, see here the charge is moving into the page, which is indicated by this X, then your fingers will curl in the direction of the magnetic field lines. And for a negative moving charge, the direction is the opposite direction that you get from using this rule. So just like electric fields, if we have multiple sources of magnetic field, then the total magnetic field at any point is just the vector sum of the magnetic fields created by the individual sources. And this is called the principle of superposition. So now we're going to try to find a formula for the magnetic field created by a section of current carrying wire. So let's say we have a section of wire with so its cross-sectional area is A and its length is dl. So if there are n charged particles per volume, and each of these charged particles has a charge q, then the total charge moving in this segment of wire is n times the volume, which is A dl, times q. So this is the total amount of charge in this tiny section of wire. And so then we're going to use the formula that we just used for the magnetic field of a single point moving charge. We're going to pretend that all these moving charges in this section of wire are a single point charge with a charge of dq given by nqa dl and moving at the drift velocity. Remember, the drift velocity is the small velocity that electrons move in a conductor when there's an electric field present. So using the formula, we get that the magnetic field due to this tiny section of wire, so we call it dB, is equal to mu naught over 4 pi, and then the charge is dq, and then v cross hat, that would be the drift velocity times sine of theta, and then over squared. And so if we plug in this expression for dq, then we get nqvd adl sine theta over squared. And so this expression, n times q times the drift velocity times the cross-sectional area, we know that that's the definition of current. Now that's kind of an alternate definition of current, so we can replace all these terms with I, the current in this small section of wire. And so then we get mu naught over 4 pi times I dl sine theta over squared. So now we have a general rule. If we just replace the sine theta with the dl cross hat, where hat is again just a unit vector that points from the conductor to the point where we're trying to find the magnetic field, then we get this expression, which is called the Law of Bio Savart. And so, if we want to find the magnetic field due to any current carrying conductor, then we can use this expression. And so this is only for a very small section of a wire. So if we wanted to find the total magnetic field for a longer section, then we would of course integrate both sides. Because if we integrate dB, then we get the total B. So next we're going to look at a couple formulas that you can derive using this Law of Bio Savart. But I'm not going to derive them in the video, but that's where they come from. So if we have a long straight current carrying conductor, then the magnetic field at a distance away from this wire is mu naught over 2 pi times the current divided by And in this case, is measured always perpendicular to the wire. It's always straight above the wire. And so also, if we have a current carrying circular loop, and this coil has n loops with radius, and this radius of the circle is a, then we can find an expression for the magnetic field along its axis, which means kind of this line through the center. So at any point through this, on this line through the circular loop center, then the magnetic field only has an x component, as you can see here. And that's because the y components are going to cancel out, because the top half of the circle and the bottom half of the circle, the vertical components of magnetic field were cancelled out, and they only have the x components left. So the expression for the magnetic field in the x direction at a point along this line is mu naught times n, the number of loops, times the current times a squared over 2, and then x squared plus a squared to the 3/2 power, where x is the distance along this line through the circular loop center, and a again is the radius of the loop. And so the magnetic field is a maximum at this point here, right at the center of the loop, and this is where x equals 0. So we can plug in x equals 0 into this expression to get the magnetic field at the center of this loop.